Hello, this is Audrey Munger, and this is my Lab 5, which I chose to do on the video of the Falling Slinky. So going into the introduction and purpose section of my lab, the main purpose of this lab is to predict the motion of a slinky as it falls towards the earth. I will also analyze why a slinky is different than a typical falling object. I use Tracker to record the position of the slinky and the observed model, which I got from the video provided. I used a glow script code to make a computational model of the slinky's predicted motion. And the main results from these two models is that the bottom of a slinky remains stationary as the top falls. However, this did look slightly different in the computational model versus the observed model, and I'll talk more about why that happens. And for this lab, the system is the slinky and the surroundings are the earth. Now we'll look at some fundamental physics principles that apply to this lab. The first one is Newton's second law, and we can derive a version of Newton's second law to get the momentum update formula, which is change in momentum equals force times change in time. This is an equation that's a bit more applicable to the experiment. The second physics principle is drag force, which acts in the opposite direction to the motion of the system. And because we're dropping the slinky outside, this can also be seen as air resistance. And the last physics principle is gravitational force, which the force of gravity equals mass times the gravitational constant on Earth. And this is seen as the mass of the Earth attracts the mass of the slinky towards it. Now looking at my observed model on Tracker, I used the slinky video provided in the lab instructions and uploaded it to Tracker. I tracked the position of the bottom of the slinky through each frame of the video. And the results of this show that the bottom of the slinky does not start moving downwards towards the earth until the top of the slinky has moved down. Now looking at my code on GlowScript, you can see some of the fundamental physics principles I mentioned earlier implemented into the code, like Newton's second law in the bottom left square. You can see that I added the mass of the slinky that was provided from the video, and then also put in the initial vector for position and velocity of the slinky into the code. I also have two while loops in my code, one for while the bottom of the slinky is stationary, and one for when the top and bottom of the slinky move down together. Here is a graph of my results. The red line represents the computational model, and the blue line is the observed model. The results have a fairly similar overall shape between the red and the blue. However, there's slight differences. This could be due to the observed model having human error from tracking, or other forces like wind, because the slinky video was outside, may not be accounted for. We can see that most of the changes in the graph are in the observed model. So now, in conclusion, we know that the observed model shows slight differences from the predicted motion because it accounts for more forces than were in the computational model. Newton's second law does not accurately predict the slinky's motion because the net force is not equal to 0. There are multiple forces acting on the slinky as it falls, so it can't accurately be depicted with Newton's second law. And finally, the observed model may have more forces acting on it, like the wind, that are not seen or accounted for in the experiment. Thank you for watching.